I honestly don't remember if I've got the spectroscopy background information for Lydia and Duke online. Everybody else should have it because you had me for first semester, like the spectroscopy packet stuff, okay, that summarizes everything you're supposed to know. So I'll try and make sure that's up there, and I'll probably email you guys directly with it so that you have at least my version of it. Okay? Because it abbreviates, I think, a lot of it. It takes the 2 chapters in the textbook and turns it into, instead of 2 chapters, 80 pages, it turns it into 4 or 5, maybe 6 or 7. So the big things for spectroscopy right now, since we're looking at our acid derivatives, really what we need to address would be the big functional groups that are going to jump up in our IR. So first and foremost, the carbon-oxygen double bond will show up, okay, at 1700 is the ballpark for that. You will find, depending on who you reference, that you can tell the difference between a carbon-oxygen double bond that belongs to an aldehyde, a ketone, an acid, an ester, acyl chlorides. And yes, technically there is a difference. Okay? You're looking at a signal for the carbonyl showing up anywhere from 1730 to 1650. Okay. 5 to 6 different functional groups for a carbonyl showing up in less than 100 inverse centimeter difference. You're looking at a difference between 1710 and 1700 being ketone versus aldehyde. You don't get that resolution on these. It doesn't make sense to evaluate the difference between those functional groups based off of where the carbonyl shows up. Okay? So what you should do is just recognize you have a carbon-oxygen double bond because there's a big, tall, tense peak about 1700. The next part would be for our carboxylic acids is that we should see an OH bond. Right? The OH bond, you should remember, shows up about 3400. Okay? That's if it's just a standard OH, okay, like an alcohol. Is this a standard OH? No, because it is next to a carbonyl. That changes the chemistry of the hydrogen, making it very, very acidic, which then means that the bond connecting the oxygen and the hydrogen changes energy. It becomes much, much weaker. As the bond becomes weaker, what happens to its signal? It shifts to the right. It shifts to lower frequencies. So yes, the OH for an alcohol shows up at 3400, but for a carboxylic acid, it shifts significantly lower because that hydrogen, that bond is very, very weak. Okay? And where it shifts to is right about 3000, okay, is where it gets centered. So if we take a look at the 3 examples, the top one's a nice clean version of it. You have the OH. Notice that there's a bunch of other stuff spiking in there. Why is there a bunch of other stuff? 3000 has a bunch of things showing up. Just because the OH shows up there doesn't mean the other stuff doesn't show up. It also shows up. So it usually turns that range into just a mess. Okay? Again, the top one is the cleanest of those examples. If we move to the bottom ones, what happens? The one to the left isn't too bad. There's still kind of a nice peak there. The one on the right is in there, but it becomes less apparent. Okay? Really what you're looking for is that probably 2100 to about 2800 to be either flat, in which case there's no OH hidden there, or if for some reason it slopes upwards at a surprisingly steep angle, that's likely due to an OH. Okay, kind of makes sense? So it's not perfect, but it can show up there. If you look at it and you're like, God, that looks awful, it's probably because there's a carboxylic acid. If you look at it and go, oh, that looks kind of normal, it's probably because there isn't a carboxylic acid there. Make sense? Okay. So that's kind of what you would expect to get out of the IR. After that, your HNMR. Your HNMR looks for hydrogen. So we might expect to find the hydrogen from our carboxylic acid in the spectrum. And if we look at what you're told to memorize, you're told to memorize at 12 ppms, you would expect to see a signal there. More often than not, you don't see it. Okay. Why would it disappear? Because it's acidic, right? Meaning the hydrogen is attached to the structure and not attached to the structure. Which means, remember what NMR is doing is saying, where's the hydrogen? Okay, where's that hydrogen located? What's its chemical environment? Okay, so what's near it? If it's an acidic hydrogen, what's near it? Well, it's possible nothing is near it. It's possible that it's now very close to the oxygen. So it has a large effect with that oxygen. Which means when the instrument detects that particular hydrogen, it detects it at a large range of chemical shifts, not at a single spot. Which then means what happens to the signal? Sort of smaller. The intensity of the signal is smaller. The area underneath the curve is the same. And what ends up happening is we see, okay, so notice that there's a nice clean one. It may start to detect at 11 ppms, but it doesn't detect a whole lot. It starts to detect increasingly more and more and more till about 12, and then it stops detecting them out to 13. And so the signal that we see, if we're lucky, is this very small bubble. Okay? Because those hydrogens are all at slightly different chemical environments, which means they get different chemical shifts, which means it becomes very difficult to see that signal. Kind of makes sense? Okay. In my experience, nobody in a testing situation is evil enough to give you the NMR spectrum for a carboxylic acid where they have not explicitly shown the carboxylic acid peak. Okay. So if this was on a test, what you would see is the one in red, not the one I've got shown in blue. Okay. Because if we have the one shown in blue, whoa, okay, what it looks like is something more along these lines. Well, can you really tell there's much of a peak there? And quite arguably, you would end up ignoring it and not seeing it altogether. Okay. In my experience, everybody tests by showing the clean signal there. Okay. Usually the way that's done, digitally. Because when you run the spectrum, it doesn't show up cleanly under most circumstances. Okay. If we run carbon NMR, we will see a signal for the carbon-oxygen double bond. It says less than 200 ppms as opposed to the 200 that we would expect for aldehydes and ketones. Why would it show up less than 200 and not at 200? Still a carbon-oxygen double bond.
Because the hydrogen is the same thing as the H or the ion.
I kind of like that idea, except that I'm looking at carbon NMR, not hydrogen NMR. I was actually going to go there first too, and then you started talking, and I was like, actually, yeah, I was wrong. It's likely due to those oxygens doing some kind of resonance effect, okay, which changes the chemical environment of that carbon. Okay. It's going to make it more shielded, which shifts it further to the right, okay, because those electrons can share in, making that carbon less positive. That's going to shift it to a lower ppm. Okay, kind of makes sense? So those are your kind of big points to get out of your spectroscopy for your carboxylic acids. And unless you guys have questions, I don't have anything else to add about that. Okay. So carboxylic acids are ultimately acids. Right? So what we need to be aware of is those acid-base definitions. Your Bronsted-Lowry definition is going to be the most relevant because we're looking at them acting as proton donors. They tend to be very poor bases because we would have to have electrons to donate. Okay. The electrons from one of those oxygens are occupied via resonance. The electrons on our oxygen out here are occupied into resonance, so those aren't particularly basic. If we look at the pi bond or the lone pair on the other oxygen, okay, we're now minimizing or making the carbon more electrophilic by having those electrons go out to react with an H+. Okay? So it would make the structure more reactive. Okay? That's not generally a good idea. Okay? So if we're looking at the activity for this, your carboxylic acid will act as an acid, which is a proton donor. Okay? The flip side that we would typically look at under these circumstances would be the Bronsted-Lowry base, which would be the amine. Okay? Typically, when we talk about this section, we talk about the amines as well. Okay? That's the standard way to look at it. The amines are basic. Those hydrogens aren't acidic on the amine because we can get all sorts of fun answers on here. Right. We could look at the stability of the conjugate base. Is that a particularly stable structure? Why not? It's charged. Why not? I don't accept resonance yet. Size. The atom holding the charge is small, nitrogen. Electronegativity. Nitrogen is electronegative, but not as electronegative as oxygen. Okay? Oxygen, if we looked at water, wasn't a strong acid. Okay, it was a weak acid. Nitrogen is less electronegative than that, which means it's going to be less acidic. Okay? So that's not very good. We could bring in a resonance argument that works for the carboxylic acid, but we don't have resonance for the conjugate base of the amine. Okay? So resonance doesn't help it out to stabilize it. We could look for an inductive effect. There isn't an inductive effect. Okay? We could look for hybridization. Okay? Nothing really stabilizes that conjugate base, which would suggest that that nitrogen, or the hydrogens on the nitrogen, which I'll go through and call red hydrogens, are not acidic. Okay? So we don't have any evidence to support those being particularly acidic, based off of structural analysis that we're used to. Okay? The other thing that we've kind of skipped and glossed over, but have talked about on multiple occasions, is quantifying it. We could look at the quantified pKa value for an amine, and the pKa value for an amine is you're up in that 34 to 36 range. The pKa for the protonated amine is 9. Okay? So if I put a hydrogen on there, then it would be acidic, okay? Because I have a charged nitrogen and I want to become uncharged. Okay? Since I don't have that extra hydrogen, I'm talking about the red hydrogens there. To remove those, I'm looking at a pKa of about 34 or 36. Water's a 16. Water's barely acidic. 34, 36. That's a little bit higher. I mean, what is that? 10 to the 20th higher, okay, as far as pKa's. Okay, that's a pretty significant difference. Okay, so the amine is not acidic. Okay, it is basic because no. CH4, not acidic either. Horrible acid. Horrible base. Why is the nitrogen a base, but then the carbon is not? How can it accept protons? It has lone pair electrons. Those lone pair electrons are what make it basic. Okay? So that kind of rule of thumb that you did back in 152, well, it's a strong acid, so it's a weak base. Right? That's not a true statement. If it's a strong acid, its conjugate base is a weak base. You're looking at the partners. It's not the same compound. So that species is not a strong acid, right? That doesn't mean this species is now a strong base. Its conjugate base is now a strong base. But we aren't looking at the conjugate base. We're looking at that structure. Okay? So be very careful with your referencing to make sure you're applying your rules appropriately. Okay? You could get away with it in 152 because they always partnered things. You didn't have to worry about actual chemistry. You just had to worry about one reaction. And in the one reaction, it was only two things. Okay? Okay. So how do we know we're looking at an acid-base reaction? Well, the only thing that has changed is the transfer of a hydrogen ion. If that is true, then it's an acid-base reaction. Okay? Officially Bronsted-Lowry acid-base reaction. So we take a look at the top reaction there. What happened? Just the transfer of a hydrogen. How? Okay. We look at our reaction and say the most reactive thing there is that positive charge on the oxygen. How do I stabilize that? Let's take electrons from the hydrogen. But then I'd have a positive hydrogen. How do I stabilize the positive hydrogen? Electrons from our other oxygen. And we've now done a transfer of a hydrogen, beginning to end. That's simply an acid-base mechanistic step. What happens with the bottom one? Okay. And just to be extra obnoxious, while you think about that, there's I, and H. Okay, so we'll have to adjust the screen a little bit, because otherwise my extra obnoxious thing didn't help. Right? Did we transfer a hydrogen? Yes. Is this an acid-base reaction? No. Why not? It wasn't the only thing that was transferred. So beginning to end, this is not just an acid-base reaction. What kind of reaction is this? It's an addition. Okay? If I look at the mechanistic steps of said addition, do I have an acid-base step? Yes. Okay, but the reaction itself is not an acid-base reaction. Okay? Okay. So, can we alter or affect the strengths of our acids and bases? Okay. We've got our list. Okay. The one thing that's kind of missing on both of these lists would be the charge. Charge should be the first thing we look at. So it's charge followed by size, followed by electronegativity, resonance, induction, officially hybridization. Okay. But I've got one set in red and one set in blue. Why all of a sudden are we now saying there's twice as many rules? There aren't. It's the same set of rules. But the red one says size bigger is stronger. The blue one says size smaller is stronger. Those are opposites. Why are they opposites? Okay. We're applying those rules to different definitions. The red one is looking at the stronger acid. Okay. The blue one is looking at the stronger base. Because the definition changes, how we apply the rule changes. Does that make sense? Okay, so you're still applying those same 5 things. Here is just kind of a cheat, if you will, because it's now saying if you're looking at base strength, size you want to be smaller. Okay? Electronegativity you'd want to be lower, to be a stronger base. Okay? In both cases, you are doing a comparison. We don't just look at a structure and say, is that a strong base? Okay? It could act as a base. It could also act as an acid. Okay? When we're looking for applying these acid-base rules, it's rank the following structures according to acid strength. Okay? That is officially a first semester question. Which of these is the strongest acid? Second semester makes it more difficult, and we ask, What's that? More? Why? No, because we should have answered the why in first semester too. The new question that comes out of this is which is the stronger base? Okay. Most people tend to get tripped up because they memorized what was in red, okay, what the cheat sheet was, and then start misapplying the rules. Keep your definitions straightforward and then apply your definitions to those rule sets. Make sense? Okay, so ranking acidity. We got 2 compounds up top. We got 3 in the middle and 2 at the bottom. Go through and rank for acidity. One is correct. Okay, so what we're evaluating is we're looking at our difference. Our primary difference is that oxygen versus the nitrogen. Okay. So we're now trying to evaluate what would happen because it's that didn't erase quite as well as I had hoped. We're looking at the stability of the conjugate base. Okay, so we'd start with charge. Same charge. Then we move to size. They're the same. Nitrogen and oxygen are in the same row. Then we move to electronegativity. Which one's more electronegative, oxygen or nitrogen? Oxygen, which means what is it doing to its electrons? It's holding on to them tighter, making it a more stable conjugate base, which makes the original structure the stronger acid. Okay, so our analysis here is really an atom effect and electronegativity, which I believe is rule 3 on my list officially. Okay? The next set. Where's the most acidic hydrogen? Bonded to our oxygen. So once we know what we can compare, we can now evaluate between the structures. But we have to know what we're looking at first. Okay, so we're looking at what makes those hydrogens more or less acidic. We could again look at the stability of the conjugate base. That was a bit heavy on the erasure. Okay, charge. Same. Size. Electronegativity. Resonance. Induction. Not the same. Okay, so there is a difference in the inductive effect here. What do we notice? Okay, so we're looking at an inductive effect, which got us to what, rule 5? Okay, we're looking at the presence of fluorines versus no fluorines. Well, what is fluorine? The most electronegative element on the periodic table, so what does it do? It draws electrons into the structure. So it's going to steal electrons from that carbon, which will steal them from the next carbon, which will steal them from the next carbon, which will then cause those electrons to be drawn into the structure, making that more stable. Okay? The same thing would happen with the one on the middle, right? We get that inductive effect all the way through. Okay? So the one that we've got marked as least makes sense because it doesn't have any inductive effect drawing the electrons in. That's going to be the least stable structure. How about between our most and our middle? Why is the most more stable than the middle? What's the difference? There's an extra fluorine. So what is that fluorine also doing? Also pulling on the electrons, which pulls on the electrons, which pulls on the electrons, which pulls on the electrons. Meaning, even more so are the electrons drawn into the structure. Does that make it more or less stable? Makes it a more stable conjugate base, which means stronger acid. So I agree. That will be the most acidic, followed by the one on the far left, followed by the one in the middle. That ranking is good. Last one. Where's our most acidic hydrogen? Connected to our oxygen at the end again. Right. If we're going to evaluate our conjugate base, putting that negative charge there. Okay, so we run our system starting with charge. Is there a difference? No. Size, electronegativity, resonance. Don't say no. Yes, there is a difference. Okay, what is that difference? That can be a bit tricky to see. So let's just look at the carbon, because we're really evaluating the difference between where that nitro group is located. So let's see what those electrons could potentially do. Okay. And ideally, what do we want them to do? Actually, no, we're just going to ignore that. Okay. I could move it bond to atom, bond to atom, bond to atom, or bond to bond all the way around. Well, that didn't do anything particularly useful. Okay. So we could go bond to bond and then say bond to atom. Okay, putting a negative charge here, negative charge, right? Do I want to do it that way? I changed my mind. Let's not do it that way. The issue here is knowing what that nitro group is. What is that nitro group? As a hint, the nitrogen is what's connected to the structure. You mean I have to know this? Yes. That has NO2. Is that correct?
Just one double bond.
Just one double bond. Why? You've exceeded the octet by putting in two double bonds. Okay. That second double bond, where would we expect those electrons to go? The nitrogen or the oxygen? Why the oxygen? It's more electronegative. Okay. Why is that particularly relevant? What is the reactivity of the nitro group? We have that positive nitrogen. How could I neutralize that positive nitrogen? We could attempt to bring in a nucleophile. We'll notice that that will be problematic because that would exceed the octet on the nitrogen. Right? You're looking at changing the structure. The whole point of this was not to change the structure, right? Our point was to rank the acidity. So I don't want to do anything out there that changes the identity of this compound. What could I do that does not change the identity of the compound? Resonance. What electrons do I want to move to stabilize that positive nitrogen? What's that?
The pi bonds inside the cycle.
Right. So one option are the pi bonds within the ring. So we could move those out. What's the other option? Is that a valid arrow move? You're shaking your head no, Sam. Why?
Because we're breaking the octet.
No.
Or we're not. Oxygen's not made of fill. Yeah.
Oxygen is more electronegative than nitrogen. That's not going to happen. So I can't move that pi bond. What else could I do?
If one pairs from the negative oxygen.
I could do that. That would be fair game. That doesn't do anything with the rest of the structure. So that purple resonance is useless. Okay, that doesn't get to what we're trying to find out. Okay, did the green one affect that negative charge at all? Okay. I always tell you to never do this. Whoa, that was, yeah, never erase too much part of your structure. So we're going to take, I don't have to do that anyway. I'm going to take those electrons and we're going to put them on that oxygen, or that carbon. We could even put them into a double bond between the carbon and the nitrogen. That is a possibility. Okay. Did that affect my negative? The negative I'm concerned about is the red negative on the far right. Okay? But what could I do that begins with R? I could do more resonance. Right? Does that affect my negative? No. Right, then what else could I do? I could do more resonance. So what we'll end up finding is that I can build a positive charge at those positions. Yeah? Everybody see that? How about with the other one? These electrons could shift in. Which means I'd have my lone pair here, and I'd have a positive there, right? Okay. And I could shift bond to bond, yeah? Which would show that I could build a positive charge at this position, and this position, right? So, do we see a difference? Okay. What does that difference mean for us? Which would place the electrons where? Which means we'd exceed the octet. What charge is building on that carbon? Does that help any? If I bring a positive carbon near another positive carbon, it becomes less positive. If you have money and I give you more money, you have less money? It's the opposite. It makes it more positive. What does that mean? Makes it less stable. Which structure is more stable? The one on the left. Okay. So we can attempt to use resonance to help us manipulate these structures. Sometimes it's obvious, sometimes it's not. Push them around and see what happens. We may come back and talk about that one. Carboxylic acids and amines and pH. Carboxylic acids act as what? Acids. Amines act as bases. Right? So I could have a structure that has a carboxylic acid and an amine in it. Okay? What else am I listing on this slide? pH. What does pH talk about? Hydrogen concentration where? In water. So in our solvent system. So if I asked you to draw the molecule shown here in water that was acidic, a low pH, would that be the appropriate structure to draw? What? I know, it's not an easy one. Particularly because I think I screwed up the last one. Okay, what do I mean by that? Well, I'm in a solution that has tons and tons of acid in it. Okay, so if I'm in a really acidic solution, what would I expect the protonation state for my carboxylic acid to be? If I add acid, what should it do? Should it have the hydrogen or not have the hydrogen? Should have the hydrogen. So that part of the structure makes sense. How about if I'm in an acidic solution? What should happen to my amine? It should be in its protonated state. Is that the protonated state for the amine? No. So if I'm at low pHs, this is better written with that extra hydrogen. H+. What if I'm at neutral pH? Right. So now let's just say, get rid of the solvent altogether. Don't even want to look at the solvent. What would be the best structure to draw? Should it be drawn as is? And hint, if we move to pH 7, it helps us out. What is this functional group? What does it act as? What is this functional group? What happens when you mix an acid with a base? They neutralize each other. So what needs to happen? In a neutral system, that's going to be what happens. You have experienced this, how should I put it nicely, uncomfortable situation in the homework already. There was a question about what happens when you add lithium aluminum hydride to a nitrile structure. I believe you had something like this. You had LaH followed by H+. That look vaguely familiar? And then, yeah, when you went through and did your answer, you had to write NH3+. You're like, well, why the hell do I have to have that plus on there? Right? Doesn't LaH just reduce away the pi bonds? Yes, it does. It would reduce away the pi bonds to take you to NH2, which is probably what you put in at first. You're like, well, why is it wrong? What is NH2? A base. What did you add in step 2? An acid. What's going to happen? It's going to protonate it. Okay? And this is an unfortunate thing that I think most organic chemists seem to screw up pretty thoroughly, including myself, is that we can't decide what we want to test on. Do we want to test on the fact that you understand that LaH does the reduction to the amine? Or are we testing on the fact that you know that it does the reduction and that the product you produce is a base that would react with your secondary conditions? There's 2 levels that we can look at. One is admittedly hard because you have to know the chemistry. The second one is hard because you have to know the chemistry and realize that you have secondary chemistry on top of it. We've never done that before, like, I don't know, esters in the presence of Grignards. In the lab, for those of you in the lab, what happened? They reacted twice because we formed a ketone, and the ketone was more active than the ester, so it reacted a second time with the ketone to get us our Grignard, or our dye. Okay? So we do have to be cognizant of our products. Are those products more active than our starting material? If yes, finish the reaction. Where it becomes increasingly frustrating, I think, both for students and instructors alike, is again, we aren't consistent on that. And particularly for an online homework system, sometimes they just test, did you understand the basic chemistry? Sometimes they test, did you understand the basic chemistry and realize that there's a bunch of extra chemistry? Right? So if you're in a situation like that, that's where it makes sense to send an email because that's where I can help out. Right? So if we go to the full deal on dealing with this, what we're really asking is you need to be aware of the activity of your functional groups and be somewhat cognizant of this concept of pH. Okay? And remember, I said we could have answered that question if we just said pH 7. Okay, ignore the solvent altogether. So that means the solvent isn't doing anything. At a pH of 7, is that more basic or acidic than my acid functional group? That is a more basic pH, okay? Because the pKa for a carboxylic acid is a lot lower, 4-ish, which means it's acidic. So if I'm in a basic environment, what should happen to that hydrogen? Remove it. What is the pK, and this is where this one gets hard with the base, is we have to be kind of cognizant of its pKa and pKb's. What we're concerned about here is the protonated state for that nitrogen, the ammonia. Okay, the pKa for that species is 9. Okay, so when we're asking ourselves this question, really what we're saying is let's put the hydrogen on and now evaluate the pKa. The pKa for that species is 9. If I'm at a pH of 7, am I more acidic or more basic? Is my environment more acidic or more basic? It's more acidic. pH of 7 is lower than a pKa of 9. That means keep the hydrogen on the structure. Does that make sense? Okay. That's confusing. Really, really easily confusing. Easily confusing. Awesome choice of words, Mike. Okay. And we might say, well, thank goodness we don't have to stress about this because in OChem we tend to simplify things and not look at more complex structures, at least within undergraduate OChem. And you're right. We don't tend to stress about structures that have both of these functionalities in them. Except that several of you are going into pharmacy. Several of you are going into medicine, which means several of you are aiming for a biochemistry course at some point further on down the road. What was the name of the blue functional group? What was the name of the red functional group? What is the name? It is an amino acid, which becomes relevant because proteins, which is a huge part of biochemistry, looking at protein synthesis, how they are involved in other mechanistic steps. You're responsible for knowing what happens at what pHs in the different protonation states for those. Depending on the level of biochemistry that you go through and take, which admittedly is probably going to be a lower level biochem, you'll only see it as kind of an initial test question, what happens to the structure or what's the charge on the structure at pH 2, 6, and 12. Okay? And then you're done with it. If you took a more advanced biochemistry class, we can take advantage of that charge state because we can now separate it, much the same way that we did in lab, in the extraction lab. How do I remove or separate benzoic acid away from aniline? If those are in the same container, how do I separate them away from each other? I agree. We could add a base. What will the base do? It'll react with the acid to make a negatively charged structure. What does the base do to the amine? Rhymes with something. Thank you. Nothing. One of our structures is negative, one of them is neutral. What do we know about negatively charged structures? They tend to be water soluble. I can now separate these two. One goes into the organic, one goes into the aqueous. Sweet. I can separate compounds based off of their acid-base characteristics. What can we do with amino acids? I can separate amino acids away from each other depending on their acid-base characteristics. Right? Other things that we can evaluate, if we change the pH, what happens to the structure? Simple answer. It changes. If the structure changes, what happens to the function? It changes. So if we consider all living things, do I want living things that have lots of pH changes? Why not?
All that change to occur.
If I've built a hammer that works at pH 6 and I make it now pH 4, the structure of that hammer changes. Is it a hammer anymore? No, it turns into some goopy mass of nothingness that I can't do anything with. Okay? Same thing happens in cells. Okay? All life as we know it functions at a roughly narrow pH range. It's not always the same pH. Most life is narrowed right around 7. Okay? But you can get some going as low as 2 and some going higher. Okay? But even within the ones that are outside of 7, they stay at pH 2. You take that cell that's at pH 2, that lives at pH 2, and you put it in a pH 7, it's dead. Okay? It can't deal with that pH change because everything is designed structurally around that charge state. You change the charge state, everything changes. All of the intermolecular forces changing, and everything falls apart. Okay? So, carboxylic acids, that's our, I think I only spent 5 to 10 minutes on that, so that's not too bad. 5 to 10 minute overview of what you can expect to see in biochemistry. What you're applying is your knowledge of OChem and pHs and the different protonation states. Okay? The one that's tricky, amines, you have to realize are in their deprotonated state. Carboxylic acids start in their acidic state when we draw out their structures. Okay? Lower left-hand corner gets us the relationship we just talked through. If the pKa is lower than the pH, I'm saying I'm in a more acidic environment. So, sorry, if the pKa is lower than the pH is our environment. I'm saying I'm a more basic environment. Okay? So, remove the hydrogen. It's a basic environment. Get rid of the hydrogen. It needs to be the deprotonated state. Okay? So you need to be familiar with what the protonated, deprotonated states are and what that means ultimately for the charges in the structure. That then applies out to biochem. Okay? If you're interested in that, I have a funny little video on that I could send out that went through and did it because a former biochem student asked about it. And I thought it was interesting. Anybody know anything about amino acids? I'll just kind of spell this out because I think it's funny. No one knows anything about amino acids? They're proteins. Do you know there's like symbols for the amino acids? Yeah, so if I wrote S, you would know serine, good. C, cysteine. I think it's alanine. I think that one's alanine.
It's a little rusty.
This is the video I did. That was my amino acid, and I looked at the protonation states for each of the amino acids. Just because I thought it was funny. I have to share. Okay, in any case, focus. Candy. Polar pi bond with leaving group attached. So, this is now going all the way back to our mechanisms. If we have a polar pi bond, our carbonyl, and that carbon has a leaving group attached to it, okay, that changes the chemistry of the carbonyl, and that's where we get our nucleophilic addition followed by our elimination. So if we look at the breakdown, what happened in the first step? We did an addition reaction. What did we add? A nucleophile. So there's our nucleophilic addition or nucleophile addition. We form this structure. Okay. What is special about the carbon in comparison to the starting material and the product? It is a tetrahedral carbon. It gets referred to as our tetrahedral intermediate. So anytime you go through and do a nucleophilic addition elimination reaction, you should be showing, particularly if you're asked to do a mechanism, show the tetrahedral intermediate. If you're not asked to do the mechanism, do all sorts of shorthand, whatever you want to do. Right? And I'll show that shorthand in a second. Okay? What's happening in the second step?
The electron from the oxygen moving back down.
Okay, the electrons come back down to form a pi bond. We made a pi bond. That's known as an elimination reaction. What did I eliminate from the structure? Well, yes, a leaving group, but a negatively charged species, also known as nucleophiles. So what we're really referencing within this section is the nucleophilic addition followed by an elimination. The shorthand for our mechanism, this is where everybody's like, oh, this is awesome. Why don't we just do that? Because it's not right. The nucleophile comes in, attacks, look at this, nucleophilic addition, break the pi bond, followed by the elimination. And the result is we have a horrible, horrible mechanism, but we have the proper product. Okay, make sense? Depending on the identity of the nucleophile, and this is something that we have to be careful with, we could have resulted in a more active structure than what we started with. If our leaving group was, say, an oxygen, that means we're starting more with an ester. And if our nucleophile was a hydrogen, we'd be ending with an aldehyde, which is more reactive, an ester or an aldehyde. Aldehydes, because the aldehyde is more reactive than our starting material, the nucleophile is now going to attack the aldehyde instead of our starting material, and we're going to get a double nucleophilic addition. Okay? Officially, it would be a nucleophilic addition elimination followed by a nucleophilic addition. The result just looks like we did two additions. Okay? Another thing to kind of be aware of, what does it look like happened? If we ignore the mechanistic arrows, what type of reaction does that look like? It looks kind of like just a straight substitution. There's a reason we don't call it a substitution. What's that reason? Because the mechanism is up here. The mechanism is not a substitution mechanism. Okay? Kind of makes sense? Okay. The structures we're starting with, polar pi bond with a leaving group attached. The ones shown on the right are our standards for these. Okay. The leaving group being shown, some of these it's less obvious, being shown kind of on the, I got it set up right, yeah, on the right hand side of the structure. All of those would be our leaving group. Are all of those equally good as leaving groups? Okay. Which one stands out at you? Charge one. What is the leaving group in the bottom one? What's the leaving group? So for sure there's an O, I'll give you that. It's a -2, not a -1, because remember as it leaves it's taking more electrons with it. Is O -2 a stable leaving group? No, because tons of charge. Okay. NR2 negative. Is that a good leaving group? No, because of that negative. OR negative, or sorry, N negative versus O2 negative. Which one's better? So between these two, the bottom, which one's better? Why N negative? Less charge, good. O negative and N negative. Why is O negative a better leaving group? It's more electronegative. The next one. Why the top one? It's not size.
Resonance.
It's resonance. It's not atom size. Molecule size, I'll accept that. That's what you were saying. Okay. Top one. Size. Chloride is the largest of those. That's the best leaving group. So we're still using those same 5 rules. Charge, size, electronegativity, resonance, induction, to establish which of these is a better leaving group. Chloride is the best leaving group, so what does that mean about the black structure? It is the most reactive. Okay? The one I've drawn at the top, the highest up, is the most reactive. It has the largest distance to fall. The one at the bottom is the least reactive because the leaving group doesn't want to leave. Right? It's at the bottom, it has nowhere to fall. Okay? So we're looking at kind of establishing a ranking of their reactivities. Okay? So, kinetics and thermodynamics, how does that apply out with us for this? We've got our overall reaction shown above. If we start with an ester, what happens? Okay, so there's our ester. We go through to form the intermediate. That's negatively charged, so it should be higher in energy, right? And then our product. Okay. If we assume our nucleophile is higher in energy, what does that mean our product is? Nucleophile is higher in energy than our leaving group.
It's more stable.
The leaving group is more stable, meaning your product should be lower in energy. Okay? And now my drawing is going to disappear. What happens if I now go through and look at that drawing for the acyl chloride? How would I draw that one on? Would its intermediate really be any different? No, it's still negatively charged. Okay. Okay, we might expect the product to be even lower in energy. Why? The leaving group was better. So our drawing should be just over the top, and we get a difference only there. We should have a lower activation barrier too. Interesting. Why? So what you're addressing then is down over here. And we've already got that marked. So why would it have a lower activation barrier? We're saying it's higher in energy. Why is it higher in energy? Absolutely right. I completely agree with you. Why is the acyl chloride higher in energy than the ester? Why? That's exactly what I was fishing for, and of course, unfortunately, that was the wrong answer. Chloride is more electronegative than oxygen?
Not more electronegative than oxygen, but more electronegative than carbon. So it's still going to pull those electrons from its bond.
Well, but the oxygen is going to pull even harder on those electrons.
So oxygen doesn't have those electrons between the chloride and the carbon.
You're saying there isn't a bond between the chlorine and the carbon, like there is between the oxygen and the carbon?
No, that's not what I'm saying. I'm saying the oxygen's, yes, it will pull in those, but it's not.
So you're making an inductive argument. You're saying there's an electronegativity difference. Right. That electronegativity difference says the ester should be higher in energy than the acyl chloride. Where is induction as an argument? It's 5. It's dead last, we need to be making a different argument.
Resonance.
There's a resonance effect. Oxygen is better able to do resonance than the chlorine because oxygen can accept more than one bond. The chlorine, on the other hand, not so much. Its resonance ability is virtually nil. Because it doesn't have that resonance, now there's only an inductive effect. The ester has resonance and the inductive effect, they run counter to each other, effectively making it meaningless. The chlorine has no resonance and only induction. That makes the carbon in the acyl chloride a stronger electrophile. Because it's a stronger electrophile, it is higher in energy. Now the energy diagram makes sense. Our activation barrier becomes shorter than for the ester. Okay. If we go through and apply this out with each of the other acid derivatives, we'll find the exact same argument. Okay. That it does nicely stack with your reactants scaling upwards, your intermediate being roughly the same energy. Right? That was probably drawn horribly. It's going to be somewhere up here. Okay? And then our products also kind of stacking out the opposite direction. God, that looks horrible. Okay? So we see a favoring both on the front end to drop the kinetics. We also see a favoring at the back end to favor our thermodynamics. So by moving up that energy diagram, we have a stronger kinetic speed. We also have a stronger thermodynamic favoring for our products, okay, because of the stability of that leaving group.
On the reactant, why is the lowest ones like, yeah, because it's charged, why would it be lowest in energy?
It's the most stable of those. That negative stabilizes that carbon.
Okay.
That's really where we've been evaluating the chemistry, is at that carbon, the electrophile is the chemistry we're evaluating. So when we're looking at the reactant energies, we're referencing that carbon.
So as you move to the bottom, you refer kinetic or dynamic?
So as we move up, it is both kinetically faster, it is also thermodynamically more stable of a product. Okay, assuming the same nucleophiles. Okay. The biggest part of this that's important is the front half. The back half is much less so, because that's going to depend largely on whatever your nucleophile is. Okay. So, what's interesting about this diagram that my diagram did not have? So there's my diagram. Study, 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 the game of memory. Next diagram. Oh, it's Wednesday. Sorry, I just realized that. What's the difference?
More structures.
There's more structures. What are the more structures?
Yeah, the highs,
That's the biggest difference. Whoops. Stay. Dang it. Our biggest difference is the aldehyde and ketone. Notice where they're located. Okay? They're kind of centrally located on this. Okay? Why are they not getting discussed in this chapter like all the others? Well, they don't have leaving groups. Okay? Why are they more active than the acid, ester, amide, and the conjugate base of the acid?
they don't have resonance.
They don't have a resonance stabilization. Much the same with the top two above. The acyl chloride and the anhydride also don't have resonance stabilization. So the most reactive ones don't have resonance. The less reactive ones do. Okay? And before you start going, well, isn't there resonance with this oxygen? We just said that oxygen does resonance to stabilize. You would absolutely be right. That oxygen is stabilizing the carbonyl to the left. What did it do to the carbonyl to the right? It made it more reactive. Because of the symmetry in that molecule, yes, the oxygen does resonance, but by doing resonance, it makes the other one more active. Okay? So, we got our energy diagram. Go figure, the textbook drew it prettier than I did. Okay? But mine at least looked like a weird, scary lady. I guess it could be a man. It was curly. It could even have been me. It was a self-portrait. Stability of our leaving group. Sorry, I blame the sugar. My wife needs to come home so I can sleep. I think that just summarizes a bunch of stuff that we've already talked about. Let's just go with that. There are questions about that? Okay. So, God, this is spiraling so fast. This slide is super useful. This really summarizes the inner conversions. Okay? If we start at the acyl chloride at the top, I can go anywhere. Start reading Rainbow. I could be, yeah. Because it is the most reactive, I can go to any one of the rungs underneath it by reacting it with whatever the missing piece is. But if I start at the bottom with the carboxylate, how can I move up? That becomes a lot more difficult. Okay? Notice at the bottom, I can only move up to the carboxylic acid. Okay? And I do that by adding acid. I'm not doing any nucleophilic addition elimination chemistry. I'm just doing acid-base chemistry. And the only way I get that to work is by adding in a strong acid. Okay? I could also go down by adding a strong base, but I'm just doing acid-base chemistry for the inner conversion. Okay? If I start at the ester, the only way I can go up is through one channel. If I'm at the ester, I have to make the carboxylic acid. And the carboxylic acid can become the acyl chloride if I use thionyl chloride. Is that a nucleophilic addition elimination? When did we see thionyl chloride, the SOCl2? I've got it memorized when we talked about it. How do you not? I'm kidding. Well, sort of. I do have it memorized. This was in our quote-unquote useful substitution and elimination chapter, which was chapter 10 in our textbook. Okay. Because if we compare the carboxylic acid to the acyl chloride, what does it appear has happened? A substitution. Okay. So it was brought in the substitution because what we were trying to do is convert our alcohol functional group into a different functional group. Okay? And we didn't intentionally focus too much on how that happened. I talked about it, but I kind of just let it fall to the floor and didn't really elaborate it. If you go back and look at the mechanism, what was the mechanism? It's a nucleophilic addition followed by an elimination. Okay? Where the electrophile is not a carbonyl, it's the sulfur. Do you mean if I have a polar pi bond, like the sulfur-oxygen pi bond, and a leaving group, like the chloride, I can also do a nucleophilic addition elimination? Yes. Yeah, it is that mechanism. Okay? It's the mechanism we're talking about now. Okay? We didn't address it a lot then because we officially hadn't talked about it, and we were more concerned about the end result, it being kind of a substitution, getting the alcohol converted into something less active. Okay? but we can use that here to convert the carboxylic acid into the acyl chloride. The only reason we can do that is because of a property of the thionyl chloride. The thionyl chloride is a polar pi bond with a leaving group. Well, everything through the middle of that chart is what? A polar pi bond with a leaving group. So where does thionyl chloride fall in that chart? As a hint, it doesn't fall. It's the very top thing. Okay? Thionyl chloride is insanely reactive. Okay? And because of that, I can react it with the carboxylic acid to make the acyl chloride. And now I'm in the standard kind of category that I'm used to working with, and that acyl chloride can be used to make anything else. Okay? So a lot of what your problems will be is trying to interconvert between these. I'm starting with an amide, but I want an anhydride. Okay, well, the amide's the second from the bottom. There is no clear step up to the anhydride. I would first have to convert the amide into the carboxylic acid. Then I can go from the carboxylic acid to the acyl chloride. Then I can go from the acyl chloride to the anhydride. Okay? Yeah, easy. Okay. You're responsible for recognizing those intermediate steps and how you shift between them. Okay? If you establish that vertical ranking, and you'll notice that ranking shows up in a lot of my slides because that ranking is super important. If you can establish that and say, well, I'm starting here and I want up here, that's not easy. There's only certain pathways I can move through. That can help you limit what reactions you're doing and can help you say, I'm going up, that's not easy, I can't do this in one step. Okay. Which could just be a straightforward synthesis. I want you to go from this to this, one of your answers is one step. Wrong. It's got to be one of the other ones. Okay. So take advantage of that information. Make sense? Okay. I'm going to go ahead and stop there. Believe it or